Sorry about that. So it's a pleasure to be back here, in the MLconf venue. The first one was about 2 years ago in New York, and had the pleasure of meeting Courtney and Nick then. And since then, we've been in constant touch, and it's been a lot of fun. The most recent one was in Seattle. I was there, and again, every one of these events has just grown even more, and there is a lot more excitement and energy and new ideas. So it's always a pleasure to come back here. So today I'll be talking about the line of work I've been doing for about 3-4 years now on tensor methods. So if you think about a range of different machine learning tasks, right? So you can write down the optimization problem, right? So most of the times what you do is you run some local search method. The workhorse is stochastic gradient descent and hope for the best. You hope that after many restarts you will get to a good solution. But can we make this black box process a little more transparent? Can we ask in what scenarios can we actually resolve the non-convexity and get to the globally optimal solution? And especially in high-dimensional learning regimes where you have lots of variables, this non-convexity can get out of hand. Right? You can, in fact, have exponential number of critical points, and many of them can be bad local optima. So are there alternatives, right? Are there loss functions that actually do not suffer from bad local optima? And what are those loss functions? And how do we use that to solve various machine learning problems? And that's where tensor methods come in as a nice middle ground between very simple techniques such as matrix factorization. Right? So you're all aware of PCA and collaborative filtering. It's not a model-based framework, but it does a linear subspace dimensionality reduction, and then you're doing your predictions in this reduced dimensional space. The other end of the spectrum is likelihood and other model-based methods that try to maximize this complicated likelihood function that incorporates domain knowledge and all kinds of additional aspects. But solving that is a hard problem. Well, what we'll see is the tensor methods are best of both the worlds. You can solve them in essentially the same amount of time required for matrix methods. You can parallelize them essentially to the same degree. And at the same time, you get the quality of solutions that are globally optimal in terms of the original model estimation. So you get best of both the worlds. So that's the overall idea of where tensor methods come in. So let's dive into some of the details, right? So as I said, the problem of big data is challenging because we have lots of variables, right? So in addition to having lots of data, we also have lots of unknowns or variables. That's what makes it challenging. And the useful information is typically hidden as some low-dimensional structure in this high-dimensional space. Right? So it's finding a needle in a haystack. And this is challenging both from the viewpoint of computation as well as statistical guarantees. So we want to have algorithms that scale very well in terms of the number of samples and the dimension of the space. Right? Ideally, anything more than linear time is almost impractical to carry out. The other one is the statistical challenge. So if I'm trying to learn phenomena over a large number of variables, if you do not impose more constraints, you would have an exponential blow-up of the requirement of number of samples, right? So you would need a lot of samples before you get a good estimate. And this is not practical. And that's why what models and what methods can we design that do not have this exponential blow-up and require only a small number of samples to estimate. So that's what I think of as the grand challenge in machine learning, right? To do tasks in high dimensions, but in a computationally as well as a statistically efficient manner. And the computational aspect comes if you think about machine learning tasks as optimization. So almost all machine learning tasks, you can frame it as an optimization problem, right? I mean, clustering you can think of as optimizing modularity or some kind of a score that maximizes similarity within a cluster and minimizes similarity across clusters. If you think about model-based estimation, the typical rule is to maximize the likelihood of the model class, right? So find the model parameters that maximize the likelihood. And of course, if you're training a neural network or a classifier, you try to minimize some loss function, such as a quadratic loss or a hinge loss or a loss function. But what is the problem? All these problems I've listed here turn out to be non-convex optimization. But our understanding of when non-convex optimization succeeds is very minimal, right? So over the past decade or even before that, we've spent a lot of time, a lot of effort in improving convex optimization, and we have a very good handle. But real-world problems are non-convex, right? And one methodology has been to convert these non-convex problems into convex optimization, the so-called convex relaxation methods, and then hope for the best. Hope that even after doing the convex relaxation, you get to the original good solution and characterize what cases there are. But other than this, we don't really have a handle on how to do non-convex optimization, right? And by the way, I want to publicize that there is a very active Facebook page discussing non-convex optimization, both the theory, different algorithms, software code on Facebook, and I encourage you to go and subscribe. I'm one of the administrators, I'm already giving the disclaimer, but I think it's a pretty active page. So that's the biggest contrast when you think about convex versus non-convex optimization. Convex optimization has this nice property that you have the unique globally optimal solution. So if you did local search methods such as gradient descent, you're guaranteed to go to the correct solution. On the other hand, non-convex optimization has multiple such local optima. In fact, with the curse of dimensionality, you could in fact have an exponential number of local optima, right? So if you would do gradient descent and do restart, right, in principle, you can never hope to go to the correct solution because you would need an exponential number of restarts, right? And so unless you impose more structure on the loss function, this is what the general theory says, right? That non-convex optimization is what makes it challenging in high dimensions. So how do we get around this problem? So the way we have attempted to solve this is to say, let's not worry about any general loss function, but let's convert our machine learning task into one of factorizing a certain tensor. So if I think of tensor decomposition, I have a much nicer algebraic structure, and I can in fact analyze the energy landscape, and in many cases we can show that there are no bad local optima. So you can do very simple stochastic gradient style methods and get to the globally optimal solution, right? So this is really then the best of both the worlds, because we are solving complex machine learning tasks. At the same time, we are running very simple methods, and we are guaranteed to get the good solution. Of course, the caveat is in what cases is this possible, right? It's really the best of all the worlds. But let's see how to make that happen. So when you think about matrices and tensors, with modern data sets, there are indeed a large number of attributes, and the data is multimodal and multi-relational, right? So if you think about recommender systems, the simple aspect is to say there are users, there are products. But what about various other attributes of the users? Their gender, their demographics, their interests, right? So if you kind of build all those together, now it becomes a higher order tensor, right? And in a lot of scenarios, we indeed have rich data, and to encode those dependencies, we need tensors, right? So my argument is, every data is a tensor, right? Even a vector is a tensor. It's just a one-dimensional tensor. Scalar is a zero-dimensional tensor. Matrix is a two-dimensional tensor, right? So we really want to think of this general framework where I think of data as a tensor. And then we can ask what kind of manipulations we can do that can be made efficient. How to parallelize this, and how to get efficient performance. At the same time, what kind of information can I extract from these tensor objects? So the main idea is we'll use tensors to model relationships in data, right? So the one we are all aware of are matrices. So if you think about modeling pairwise relationships, so if you want to record the correlation between every two coordinates in my data, right? So if X is a vector, I can now record these correlations, right? These two-way correlations become a matrix. But now if I want to record higher order correlations, think of three-way correlations, right? I can store all this and index it appropriately in this cube, and that's my tensor object, right? So in a naive sense, this tensor is a multidimensional array, but it's more than that. You can do manipulations on this tensor. So similarly, in a matrix, if you do matrix multiplication, you can reduce a matrix into a vector, and also, if you multiply the matrix on both the sides, you reduce to a scalar, right? Similarly, you can extend those notions to tensors, and they're called contractions. And this operator notion gives us a lot of power. We can now get different kinds of information by projecting the tensor along different directions. And we'll see many of the algorithms will proceed in that light. So the main workhorse will be the extension of spectral decomposition to tensors, right? So what's the idea? I have this tensor, right? It could be a huge object. So think of each dimension of the tensor itself running into million. So it's a million cube or more, right? So you have this really huge amount of information, but you want to summarize it. You want to summarize it as sum of some small number of rank 1 components, right? So this is exactly the extension of SVD, or singular value decomposition, to tensors now. And the question is when we can do this efficiently, right? Can we actually correctly compute this decomposition? So computing this decomposition is itself a non-convex problem, but it turns out that we can analyze the non-convexity here, and in many cases, we can get to the globally optimal solution. And that's what differentiates general non-convex optimization from tensor decomposition. We can guarantee getting good solutions from this. And I won't go into the details there in our papers, but many of the operations will exploit the parallelism of linear algebraic operations. So we can build on the BLAS, efficient BLAS or basic linear algebraic subprogram libraries and get very fast speed up and run these tensor methods efficiently. The main intuition is we'll first do singular value decomposition on pairwise moments, and we can do this efficiently through random projection tricks, right? And we can, using this information, we can reduce this big tensor into a much smaller tensor. And on this smaller tensor, we can run some iterative methods to get the different components, and then we can go back. So in summary, all these set of operations are linear algebraic or multilinear algebraic methods. So you can make this very much parallelized. In fact, one of the projects I'm working in collaboration with researchers at NVIDIA is to build extensions to the BLAS kernels themselves that will provide a nice interface for doing these tensor contractions efficiently. And another project has been Farong's efforts to deploy this on Spark. So we now have a distributed implementation, and I encourage you to visit the code and contribute to it and give us ideas on how to go further with this. So we can run this now very efficiently on large-scale data. And let me just very briefly get to some of the applications of where these tensor decompositions come up. So the first set of applications we looked at was unsupervised learning. Right? Indeed, this is a very challenging problem because we have no labeled data, and we want to learn about these hidden variables. So if you think about mixture models, right? So you now have these unknown mixture distributions, and also you don't know what each sample belongs to, right? From which component mixture it is drawn. If you think about hidden Markov models, the hidden state which evolves over time is not observed. You only kind of see transitions from that hidden state, right? The ICA, or the independent component analysis, says that there's some set of hidden sources that transform in an unknown way to get the observations. So I don't know both the hidden sources as well as the transformation. I have to learn both of them. So these topic models are models for text which say that every document is a mixture of several topics. right? So these are also called admixture models. The multi-view models are models where this hidden parameterization relates different kinds of sources. It could be audio, video, text, that all talk about the same phenomena. So you want to kind of find the common embedding across these different sources. So I can build a model that encodes that. And the main framework is to take this unlabeled data, right, as I said, posit this class of latent variable models, and we'll look at tensors. So in these cases, tensors turn out to be higher order moments in data. So in the text example, it turns out to be the co-occurrence counts of triplets of words or higher in my document, right? So I can look at like every triplet of words and count how many times on average it occurs across all documents. So I can come up with these counts, and then I can go ahead and decompose that tensor. Of course, when I'm implementing it, I won't explicitly build that tensor, right? Because that's a huge tensor. But that's the principle. I'm looking at the information that's given by these higher order relationships of words in my document. And once I do this decomposition, I have the model and I can do inference. Right? And we have a series of papers where we analyze this method, and we show that it's efficient both in the computational and statistical sense. So it's guaranteed to converge to the correct model, right? So you have this global optimality guarantee when you have this population setting, right? When you go to the population framework. And at the same time, you only need some polynomial amount of time and polynomial number of samples to run this. In fact, you can parallelize it to the extent of being linear in the number of samples and the dimension of the input. So you can really get the best possible complexity of runtime. And so we have, and we have all these efficient linear algebraic libraries we can build upon, so we can make this code very efficient, right, without new work. We can build on top of existing frameworks. And so that's what distinguishes it from many other frameworks that involve general loss functions. So here we have a unified framework for training a variety of different models where the idea is to form these appropriate higher order moments. Like look at these higher order moments, which are tensors, do the decomposition. The decomposition gives me the parameters of the model, and then I can go back and do predictions using that model. Right? So that's the overall framework. The details are indeed in the papers. And we can also use this for detecting communities in graphs, like hidden communities in graphs, or in the recommender system, detecting hidden groups of users. And also it could be with multi-attributes now. We could also have tensor objects. And so just to give you some ballpark numbers, this was just run on a single workstation compared to the variational inference, which is the state-of-art method for training probabilistic models. This is much faster. In fact, it's more than 2 orders of magnitude faster, and it's much more scalable even on a single machine. The reason is if you try to do variational inference, you're looking at relaxations of likelihood function, and that loss surface can have a lot of bad local optima. So our latest thing after that has been to train neural networks. We know neural networks have had a great practical impact, but we want to go back to even the basic theory and argue that, in general, if you think about backpropagation, it can have bad local optima. So even in this simple example, in addition to the good local optima, which are these separators which reduce the training error to 0, you also have bad local optima with bad training error, right? And you can also visualize that in the loss surface, it's highly non-convex. But it turns out we can instead run tensor factorization to train the neural network, and you see that it's nice local convex in this region and has a much better loss surface compared to the backpropagation one. And I won't go into the details, but the main idea is for neural networks, you need to do a little bit more work. You need to transform the input and look at the relationships with the output. And this is the tensor that gives me the right set of weights that is guaranteed to get to a good neural network. So let me skip this. It involves these probabilistic models and the score functions, and we have the framework. There's more details in the papers. But the main idea is now I'm turning the problem of training a neural network into one of tensor decomposition. So I obtain the weights of my first layer through tensor decomposition, and then I can recurse. Another framework which we've been recently investigating is reinforcement learning. So this is the challenging problem where you don't know the environment you're trying to learn. At the same time, you're trying to get to some objective, right? It could be like kind of the robot like going through an unknown environment. And these models are notoriously hard to train. And for the first time, we can guarantee efficient training of these partially observable Markov decision processes. So there are also convolutional models we can train and incorporate those convolutional constraints, which is important for image and other settings, right? So we can also do that. There's also hierarchical tensor decompositions we can do and so on. So let me summarize by saying that tensor methods offer a nice middle ground between these matrix-based methods that do not incorporate a model and that cannot build a very complicated system compared to general optimization, general loss function that could be arbitrarily non-convex and have lots of bad local optima, right? The tensor methods can now be addressing multiple different machine learning tasks, and at the same time, you're guaranteed to get a good solution and have efficient deployment and running time because we can build upon all the existing matrix methods, and it's a simple step away to parallelize these tensor methods. And indeed, there's lots of exciting problems in this space, both in theory and practice. Since I'm out of time, I'll stop here. This is my excellent research group, and one of my students, Farong Huang, is in the audience. I'm very happy that she won the Industry Impact Award, and please talk to her about the Spark implementation and other things. She's a better person to reach out than me. And indeed, there are many more resources on my website. Thank you.